Armored ground wire, also known as AGW, is a type of cable used for grounding electrical systems. It consists of a ground conductor surrounded by metallic armor. A common question arises regarding whether AGW can be directly buried. The UL White Book does not explicitly list armored ground wire for direct burial. The National Electrical Code, or NEC, does not specifically address the use of AGW for direct burial. However, Article 250 of the NEC states that metal-clad cables such as BAG, which stands for bonded armored ground, can be used for grounding if they are approved for the intended use. IEEE STD 80 states that AGW is acceptable for direct burial if it meets certain criteria. Firstly, the armor is not bonded to the ground conductor. Secondly, the armor is protected against corrosion. Considering these points, if a utility company requires the grounding electrode conductor, or GEC, to a driven ground rod to be bonded armored ground, this requirement can be valid if the BAG meets the NEC and industry standards for direct burial. A local inspector's contention that AGW is not listed for direct burial may be incorrect. AGW is indeed suitable for direct burial if it adheres to the criteria specified in IEEE STD 80. In conclusion, AGW can be used for direct burial if it meets the stipulations outlined in IEEE STD 80. The misconception that AGW is never approved for direct burial is inaccurate. A utility company's mandate for using bonded armored ground for the grounding electrode conductor to a ground rod is acceptable under specific conditions. To further elaborate on the NEC, it's important to understand the scope of Article 250, which covers grounding and bonding. Section 250.4 A5 addresses grounding electrode system installation. This section details the requirements for grounding electrodes, including ground rods, and how they must be connected to the electrical system. While the NEC doesn't provide explicit tables for AGW direct burial, it emphasizes that grounding conductors and their enclosures must be suitable for the conditions of use, including direct burial where applicable. This suitability is often determined by meeting industry standards like IEEE STD 80, which provide more granular guidelines. When evaluating whether AGW meets the standards for direct burial, consider the materials used in its construction. The metallic armor must be resistant to corrosion or otherwise protected. Common methods of protection include using a corrosion-resistant alloy or applying a protective coating. Additionally, ensure the grounding conductor within the armor is adequately sized for the intended fault current. NEC Table 250.122 provides guidance on sizing equipment grounding conductors based on the overcurrent protective device rating. The grounding conductor must have sufficient ampacity to safely carry fault current back to the source, facilitating the operation of the overcurrent device and clearing the fault. IEEE STD 80 offers more specific guidelines for grounding in substations, but its principles can be applied more broadly to other electrical systems. This standard emphasizes the importance of minimizing ground potential rise during fault conditions to protect personnel and equipment. When using AGW, ensure the armor is properly bonded at both ends to maintain a low impedance ground path. Improper bonding can lead to increased impedance, which can impede fault current flow and increase the risk of electrical shock. Moreover, the utility company's requirement for bonded armored ground often stems from concerns about mechanical protection and resistance to physical damage. AGW provides a robust layer of protection against damage from digging, impacts, and other external factors that could compromise the integrity of the grounding conductor. The local inspector's role is to enforce the NEC and local amendments, which may sometimes lead to differing interpretations. In situations where there is disagreement between the inspector and the electrical contractor, it's crucial to engage in open communication and provide documentation supporting the use of AGW for direct burial. This documentation may include the manufacturer's specifications, test reports, and engineering analysis demonstrating compliance with applicable standards. If the disagreement persists, consider seeking clarification from the local electrical authority or appealing the inspector's decision through the established channels. Remember that the ultimate goal is to ensure the safety and reliability of the electrical system while adhering to the applicable codes and standards. When installing AGW for direct burial, follow these best practices. Firstly, prepare the trench properly by removing any rocks, debris, or sharp objects that could damage the cable. Secondly, ensure the AGW is buried at the correct depth. The NEC typically requires a minimum burial depth of 18 inches for underground cables, but local codes may have more stringent requirements. Thirdly, backfill the trench with clean soil or sand and compact it thoroughly to provide support and protection for the cable. Fourthly, clearly mark the location of the buried AGW with warning tape or other suitable markers to prevent accidental damage during future digging activities. Fifthly, perform a ground resistance test after installation to verify the effectiveness of the grounding system. A low ground resistance is essential for ensuring proper fault current flow and minimizing ground potential rise. When selecting AGW for a specific application, consider the following factors. Firstly, the size and opacity of the grounding conductor. Secondly, the type and thickness of the metallic armor. Thirdly, the corrosion resistance of the armor and conductor materials. Fourthly, the environmental conditions at the installation site, including soil type, moisture levels, and exposure to chemicals or other corrosive substances. Fifthly, the applicable codes and standards, including the NEC, IEEE STD80, and local regulations. In some cases, it may be necessary to consult with a qualified electrical engineer to determine the most appropriate type of AGW for the specific application. The engineer can perform calculations and analysis to ensure the grounding system meets all applicable requirements and provides adequate protection against electrical faults. Furthermore, consider the long-term maintenance requirements for buried AGW. Periodically inspect the cable for signs of damage or corrosion, and perform ground resistance tests to verify its continued effectiveness. If any issues are identified, take prompt corrective action to repair or replace the damaged cable. Remember that a well-designed and properly installed grounding system is essential for the safety and reliability of any electrical system. By following the applicable codes, standards, and best practices, you can ensure that your grounding system provides adequate protection against electrical faults and minimizes the risk of electrical shock. In addition to the points already discussed, it's beneficial to understand the different types of AGW available. One common type is constructed with a copper grounding conductor and a galvanized steel armor. This type is suitable for general-purpose grounding applications and provides good mechanical protection. Another type features a copper grounding conductor and a stainless steel armor. This type offers superior corrosion resistance and is ideal for use in harsh environments such as coastal areas or industrial facilities. A third type utilizes an aluminum grounding conductor and an aluminum armor. This type is lightweight and cost-effective, but it may not be suitable for all applications due to its lower conductivity compared to copper. When selecting AGW, it's essential to consider the specific requirements of the installation and choose a type that is appropriate for the environment and application. In some cases, it may be necessary to use a combination of different types of AGW to achieve the desired level of protection and performance. For example, you might use stainless steel AGW in areas that are prone to corrosion and galvanized steel AGW in other areas. Furthermore, it's crucial to ensure that the AGW is properly terminated and connected to the grounding system. Use approved connectors and fittings that are specifically designed for use with AGW. Follow the manufacturer's instructions carefully when installing the connectors and fittings to ensure a secure and reliable connection. Improper terminations can lead to increased resistance, which can impede fault current flow and reduce the effectiveness of the grounding system. In addition to the physical installation of the AGW, it's also important to consider the documentation and labeling requirements. Clearly label the AGW at regular intervals to indicate its purpose and voltage rating. Maintain accurate records of the AGW installation, including the location, type, size, and date of installation. This documentation will be helpful for future maintenance and troubleshooting activities. Moreover, consider the impact of the AGW installation on other underground utilities. Before digging, contact the local utility companies to locate any buried cables or pipelines. Take precautions to avoid damaging these utilities during the AGW installation. Damage to underground utilities can be costly and dangerous, so it's essential to exercise caution and follow all applicable safety regulations. When working with electrical systems, always wear appropriate personal protective equipment, including safety glasses, gloves, and insulated footwear. To energize the circuit before working on any electrical components. Use a voltage tester to verify that the circuit is energized before proceeding with the work. If you are not comfortable working with electrical systems, consult with a qualified electrician. Electricity can be dangerous, and it's essential to take all necessary precautions to protect yourself from electrical shock. In addition to the information provided above, consider the following points regarding the use of AGW for grounded electrode conductors, or GECs. The NEC requires that GEC be sized according to Table 250.66, which is based on the size of the service entrance conductors. The GEC must be large enough to safely carry fault current back to the source, facilitating the operation of the overcurrent device and clearing the fault. When using AGW as a GEC, ensure that the grounding conductor within the armor is sized appropriately. The armor itself does not count towards the GEC ampacity. The armor serves primarily as a mechanical protection and corrosion resistance. In some cases, it may be necessary to use a larger size AGW to accommodate the required grounding conductor size. For example, if Table 250.66 requires a number 4 copper GEC, you may need to use a 1-inch AGW to accommodate the number 4 conductor. When connecting the AGW to the grounding electrode, use a listed and labeled grounding clamp or connector. The clamp or connector must be compatible with both the AGW and the grounding electrode material. Ensure that the connection is clean and tight to minimize resistance. A high resistance connection can impede fault current flow and reduce the effectiveness of the grounding system. When installing the grounding electrode, follow the NEC requirements for depth and spacing. Ground rods must be driven at least 8 feet into the ground and spaced at least 6 feet apart. The top of the ground rod must be buried below the frost line to prevent damage from freezing and thawing. In some cases, it may be necessary to use multiple ground rods to achieve the required ground resistance. The NEC requires a ground resistance of 25 ohms or less for most applications. If the ground resistance is higher than 25 ohms, you must install an additional grounding electrode. Perform a ground resistance test after installing the grounding electrode to verify its effectiveness. Use a ground resistance meter to measure the resistance between the grounding electrode and a remote reference point. The ground resistance meter should be calibrated regularly to ensure accurate readings. Keep in mind that the utility company's requirements for the GEC may be more stringent than the NEC requirements. The utility company may require a larger size GEC or a lower ground resistance. Consult with the utility company to determine their specific requirements before installing the GEC. Furthermore, consider the impact of the grounding system on sensitive electronic equipment. A poorly designed or installed grounding system can introduce noise and interference into the electrical system, which can disrupt the operation of sensitive electronic equipment. To minimize noise and interference, use a dedicated grounding system for sensitive electronic equipment. Isolate the grounding system from other electrical systems to prevent the flow of noise currents. Use shielded cables and connectors to minimize electromagnetic interference. Install surge protection devices to protect sensitive electronic equipment from voltage transients. Regularly inspect and test the grounding system to ensure its continued effectiveness. A properly designed and installed grounding system is essential for protecting sensitive electronic equipment from damage and ensuring its reliable operation. In summary, when using AGW for grounding purposes, consider the NEC requirements, IEEE standards, utility company specifications, environmental conditions, and the specific application. Proper selection, installation, and maintenance of the AGW are crucial for ensuring a safe and effective grounding system. If you have any doubts or questions, consult with a qualified electrician or electrical engineer.